Okay, now one important aspect that we have looked at earlier, but I want to emphasize once more for completeness and for clarity. A rational transfer function, an LTI system which has got a rational transfer function, can be written in this form, a general form: A naught by B naught, product k equal to 1 through m, 1 minus ck z inverse divided by product k equal to 1 through n, 1 minus dk z inverse. Right? You are familiar with that. The poles at z equal to dk, zeros at z equal to ck, k equal to 1 through m, in this case k equal to 1 through n. Okay. Now this is the factorized form of now if you have n greater than or equal to 1, that means at least one pole is present, then h of n will be IIR. Okay, you don't have to check anything. If you compute the transfer function and you find that there is at least one pole, then there will always be an IIR. So for example, we will look at the ways by which we will quickly identify IIR systems. So supposing you have a transfer function h of z equal to y of z divided by x of z. Let's look at just one pole, 1 minus d naught z inverse. Okay, show me and obtain an implementation of this LCCDE. So LCCDE says y of n minus d naught y of n minus 1 is equal to x of n. Okay, this is the LCCDE. So implementation, take x of n, put in an adder, this is the output y of n, pass the output through a delay, you will get y of n minus 1, multiply it with a multiplier which has got a value d naught, and then add this signal to the sequence, and then you will get the input output relationship. Now notice that what we have here is a feedback loop. Okay. So here is a way by which we can identify an IIR system. One is if you see a pole in the transfer function, IIR system. If you see a feedback loop in the implementation circuit, again an IIR system. The third way that we can recognize is by the recursive equation. Okay, because y of n depends on y of n minus 1. So if you write it one step, you can recursive relation. Okay, you can write it one step and then you can look at that. So write down the expression y of n minus 1. This will be equal to d naught y of n minus 2 plus x of n minus 1. Okay, if you call this as equation A and this as equation B, substitute B in A. Substitute B in equation A. What do you get? You will get y of n is equal to d naught squared y of n minus 2 plus x of n plus d naught x of n minus 1. Okay, then you substituted one for yn minus 2, you will get x of n minus 2. Then eventually you will get it as an infinite length because it is a recursive relation. So if you see a recursive relation in your representing your input-output relationship, this is also an indication to get an that is an IIR system. So how do you identify an IIR system? at least one pole in the transfer function, a feedback loop, or a recursive relationship in the time domain when you write down the relationship in terms of the LCCD. So these are good points to keep in mind. Now I want to dive into the new topics that we want to look at in today's discussion. So we said that if you have an LTI system who's characterized by an impulse response h of n, for which we have computed the dt of t h e of j omega, we can then represent it in terms of the magnitude response, magnitude h e of j omega, or and the second way is by the argument of h e of j omega, which is the phase response. Now, how do we typically plot the magnitude response? So supposing, for example, we want to look at a low pass filter. A low pass filter, if you plot with respect to omega, typically you will plot it from the range 0 to pi. Typically what you will see is that there will be some frequencies that will be passed, and then the low pass filter will come down, and then you will see behavior like this. So this is magnitude h e of j omega. Now, what we are interested in is to look at the actual variations that are present in the response of the magnitude of the magnitude of the LTI system, and particularly what happens at low values. So this particular way of representing it using the magnitude and representing it does not give us enough insight. So instead, what we will do typically will always be to plot on a dB scale. So 20 logarithm of magnitude h e of j omega, that is the quantity that we plot, and that when we plot from 0 to pi, we get a lot more information that is present in terms of what is the behavior of the system. So for example, you may see that the system shows a behavior that looks like this. There is some variation that is happening in the stop band. So these are visible only when you look at it on a dB plot. The x-axis is always in terms of the frequency. The magnitude, the y-axis, rather than a linear scale, we always prefer to plot it in terms of the dB scale. Again, when you do experiments on the computer and you look at the behavior of LTI system, always remember that the magnitude response must be plotted in this manner. Now, let us take a quick look at the aspects of an overall system, and also characterize it in terms of the magnitude and phase response. So let's go back and let me capture this particular form. Okay, so let me use this as my response of my LTI system. Okay, now supposing I want to get the magnitude response of h e of j omega. Okay, so I want 20 logarithm of magnitude h e of j omega. Okay, so this is what I'm interested in. So I want to get the magnitude response of the entire LTI system. So this is a LTI system. Okay, so then what we do is we take the numerator and say, okay, so what are the terms? It's 20 log, by the way, it's logarithm. When I just say logarithm, it's logarithm base 10. Okay, so always keep in mind, when I don't have a base, you can take it as times the magnitude of A naught by B naught. This is just a scale factor, does not affect us. Now you have a product of terms. What we can do is, because now you're taking it on the logarithmic scale, we can add the logarithmic contributions of each of the numerator terms. So k equal to 1 through m, 20 log magnitude of 1 minus ck e power minus j omega. So each of these terms, you can take the magnitude response and then you can add it in the logarithmic scale. but in the linear scale it will be multiplication. So keep that aspect in mind. Now what about the denominator terms? The denominator, when you take logarithm of a ratio, numerator gets added, denominator gets subtracted. So you subtract out the denominator components. K equal to 1 through n, 20 logarithm base 10, 1 minus absolute value of 1 minus dk e power minus j omega. Okay, that is one of the advantages of the factorized form. So what we are going to be sort of working towards is saying, supposing I have a LTI system which is a second order system, I can always look at these first order systems and see how they will affect my magnitude and phase, and then add the first order system responses together. So the study of first order systems and second order systems are very important for us, because ultimately we can use that as the building block. Okay, so this is the one. So then you have the argument of h e of j omega, the phase response. Phase response also can be computed very simply. Summation k equal to 1 through m. Remember, e power j argument. So therefore, when you multiply terms together, the argument of all the numerator terms get added together. So it is summation k equal to 1 through m argument of 1 minus ck e power minus j omega. All the numerator terms, their phases get added together. The denominator terms, their phases get subtracted. K equal to 1 through m argument of 1 minus dk e power minus j omega. I hope you are comfortable with that. One of the general form of a LTI system, which is IIR, because you have poles here, and of course you can get a special case when FIR. So you can get this LTI system will be FIR if n equal to 0. That means there are no poles. The denominator is equal to 1, and therefore the FIR becomes a special case. The most general form is given here. When you want to get the magnitude response, you're looking at the numerator terms adding together, denominator terms subtracting, and the same behavior you also see for the phase term. And finally, if we are interested in a group delay, remember, we must be working with the unwrapped phase. Okay, so we then get tau omega as minus d by d omega argument of h e of j omega, the total LTI system's response, but it must be the unwrapped phase. Okay, only then we can get the group delay. Unwrapped phase. Okay, I hope you are comfortable with that and are able to appreciate. So now what we are going to say is we are going to really zero in on first order systems, because first order systems basically, as you can see, are the building block. You have m first order terms in the numerator, n first order terms in the denominator. We can then look at the overall behavior in the following manner. So magnitude response of the LTI system, let us take a quick look and look at. So supposing I have a first order system, h of z equal to 1 minus C1 z inverse. C1 z inverse. Okay, so basically what we are saying is we want to look at the behavior of this particular system and look at so let us say that C1 is real. Okay, so then we can expand this as h e of j omega 1 minus C1 e power minus j omega. This can be written as 1 minus C1 cosine omega plus j times C1 sine omega. C1 sine omega. Okay, so this particular segment of the lecture is going to involve a lot of trigonometry, so I will write it down, but do take time to make sure that you are able to verify these results. So magnitude He of j omega magnitude squared will be 1 minus C1 cosine omega whole squared plus C1 sine omega whole squared, and if I want to get only the magnitude, then this will be square root. Okay, so you can now how to get the, for a first order term, how to get the expression. Okay, now let us look at what is the argument of He of j omega. I am just showing you, I am sure you are comfortable with this, but just for so basically we are looking at first order systems very closely. We want to know how to get the magnitude, how to get the phase, how to get the group delay. All three will be discussed here. So this will be given by inverse tangent or tan inverse of C1 sine omega divided by 1 minus C1 cosine omega. That is the phase response. Okay, and I also want you to be able to compute the group delay of this So basically tau of omega will be equal to minus d by d omega of argument of He of j omega. Okay, so this is the same as minus d by d omega of tan inverse of C1 sine omega divided by 1 minus C1 cosine omega. Okay, I want you to be able to, or want you to be comfortable obtaining the expression for the derivative. Okay, so please verify that this comes out to be equal to C1 squared minus C1 cosine omega divided by 1 plus C1 squared minus 2 C1 cosine omega. Okay, so that is the expression that we get for the group delay. Okay, I hope you are comfortable with that, and make sure that you are getting it correctly. All right. Now, if we assume that C1 was real, okay, the same thing you can repeat for C1 complex. Okay, C1 complex means there will be a real part and an imaginary part, and therefore you will have to take that into account. And in this case, you can again get the expression for the magnitude. You can get the expression for the phase. It will also involve the angle of the where the zero is located. Okay, so for example, if C1 is equal to R1 e power j theta 1, okay, then what you will get is He of j omega will be equal to 1 minus R1 e power j theta 1 e power minus j omega. You can write this as 1 minus R1 e power minus j omega minus theta 1. Okay, which then you can write it as 1 minus R1 cosine of omega minus theta 1 plus j times R1 sine omega minus theta 1. Okay, again you will start to see a similar pattern. What I would like you to do is evaluate magnitude He of j omega, get the argument of He of j omega, and finally get the group delay. Okay, I will just give you the final expression for the group delay because I am assuming magnitude and argument will be straightforward. So this will be equal to magnitude C1 squared minus the real part of C1 e power minus j omega divided by 1 plus mod C1 squared minus 2 times real part of C1 e power minus j omega. Okay, so again, I'm sure that these are not difficult, but will require you to carefully go through the steps. I've shown you how to do it for C1 real. I would like you to verify these results for C1 complex. Okay, so this is a task for you to complete. Okay, so this is task to complete. How to do it for a first order system.